The previous example covered the case of a power function. So you may think that then this can only work in cases in which we have other methods to compute things almost explicitly or approximate things. They're all algorithms, say, for computing the cube root. They are very inconvenient. But so somehow I think the method of the scope of applications is better illustrated by examples where you don't know anything about the function except at certain points. So for polynomials, you just plug things in and you see what you get. And so it's kind of pointless to approximate it. But in this example, so, and this is going to be relevant later in one of in the example in the next video. Try to estimate. So estimate, we're going to be asked to estimate or find. I mean, I'm just going to use a wording that you'll see a lot. So find the best approximation of best linear approximation. So the best linear approximation of cosine of x at x equals pi over 4. So whenever you hear anything or you read any statement like this in an exam or in a question, you ask for the best approximation. It has to do with the linear approximation, the approximation given by linearizing the function. So taking the value and the derivative and using that the tangent line to approximate function nearby. And so here is the thing. Cosine of x is not a polynomial. So say from certain points like pi over 2, pi over 4, pi over 3, pi over 6, and things like that, you have no idea how to approximate cosine x. I mean, we haven't learned that yet. And even in those cases, I mean, the approximations involve iterating many steps on a kind of a cumbersome scheme. There are expressions that you learn later, such as Taylor's expansion, which converge very slowly, but in fact they're just higher order approximations of what we're going to do now. So in any case, the thing is, you don't know anything about cosine, what cosine looks like, so you don't have an explicit expression for cosine. So how on earth are we going to approximate cosine nearby? You think, oh yeah, but I need to know, I happen to know what cosine is at pi over 4. But okay, but we need the linear approximation, so we also need the derivative. But we also know what the derivative is at pi over 4. And this is the case for most functions. So for most functions, we know we know the value of the point. We also know the value of the derivative of the point. I mean, and that's one of the things I try to convey in the previous example, in the more elementary example. So what is the best approximation, best linear approximation of cosine of x? So what is L of x? So this is what we're after. What is L of x? From here, many other questions can arise. So we'll compute the value of cosine at pi over 4 plus 0.02, which is something we're going to do in sort of a related example. But so what is a linearization? For linearization, we need two things: the value of the value of the function at the point, and the value of the derivative at the point. So it's going to look something like that. So here, f of x, we identify the function, it's just cosine of x. X naught is pi over 4. Okay, so we just need to compute, so we just need to know, two things. Cosine of pi over 4 which is square root 2 over 2, or 1 over square root 2. And what is the derivative? So this is just f at pi over 4. Remember that f is cosine. What is f prime of x in general? Is minus sine of x. So f prime at pi over 4 will be sine at minus sine at pi over 4. But what is sine at pi over 4 again? Just square root 2 over 2. Well, maybe this doesn't quite look like an f, so let me just correct it a little bit. So this is all the information we need. So we need f at pi over 4, we need f prime at pi over 4, and this is all we need to get the linear approximation, the best approximation. L of x is just square root 2 over 2, which is f at x naught, and then plus f prime at pi over 4, which is minus square root 2 over 2, times x minus pi over 4. Minus square root 2 over 2 is just f prime at x naught for this particular example. So you get in the end square root 2 over 2 minus square root 2 over 2 times x minus pi over 4. And this is our approximation. So this is all our linear approximation. Okay, so this is yes, this is one example in which we can differentiate things and still know. I mean, knowing the value of the point is not enough, but usually when we know the value of a function at this particular point, we also know the value of the derivative. In exponentials is even more clear, because the derivative of exponentials have to do with the value at the point. The derivative of e to the x is e to the x itself. Of course, if you know the value of e to the x at a particular point, then you also know it. You also know the values of the derivative, because it's the same value of the function. Okay, so this is so in general, when we're asked to use the linear approximation, they may also ask you. So another question, related question. A related question would be, what is a good approximation of cosine of pi over 4 plus 0.02, say. And they will give you a number of options, maybe below. And here the way to do it is to go back to the linear approximation here. So whenever you ask me about an approximation in calculus, approximation always comes from looking at the linearized equation. So here you go back to the previous calculation, or the previous expression, and you just need to plug in x equals pi over 4 plus 0.002. So you go back here to this expression, you see that this is square root 2 minus 2, so linear approximation at that particular point will be, this is a minus square root 2 over 2, and then times x, which is pi over 4 plus 0.02 minus pi over 4. And because this is the point at which we are approximating. You see these two things cancel out, and we just get square root 2 over 2, and we can factor that out, minus 1 minus 0.02. And you can simplify this expression further, but the point I'm trying to make is when so most of the times you'll be asked to find the linear approximation, and from that question they'll ask you following the second question, related question, be to provide a good approximation of that function which you just approximated at a particular point. You just need to plug, if that's the case, you just need to plug in the value x. Just recognize what x is here. If not, I mean, they may just ask you immediately what is a good approximation of cosine of pi over 4. In that case, you need to first identify the function f, which is cosine, and then the point, which x0, which is pi over 4. But that's kind of natural. So usually you see e to the x is the function is just e to the x, and if it's cosine of x, it's just cosine. And the point, well, something you're familiar with. So if it's pi over 4, pi over 3 in a trigonometric function, then of course that has to be the point at which you're approximating. Because 0.02 is nothing special for cosine, but multiples of pi or in fractional expressions involving pi are relevant for the computation of trig functions. So that's just the general advice, and we'll introduce another concept in the next video, which is important because here we've only dealt with an approximation. We've spoken very vaguely about these expressions that we obtain here, like L of x. The things we would like to quantify how good this approximation is. We know for sure that as x gets closer and closer to the to x naught, in this case pi over 4, it gets better. But how do you know how close you need to be in order to get a reasonable approximation? And a better way to measure, rather than computing the error, so the difference between f of x and L of x, is to measure the percentage error. Because if you are computing quantities that are really, really small, so say 0.001, and then you make an error of 0.2, that's huge. On the other hand, if we were computing things that had to do with millions, and the error you make is even 10, which is kind of pretty bad for the previous example, it's actually quite good. I mean, 10 out of a million is just a pretty small thing, pretty small error. So that's what we're going to introduce next, and we're going to do some problem related to that, and to illustrate how you'd be asked to compute things involving that. So that's for the next video.